All right, hi. My name is Niv, and I'm a postdoc at the Data Systems Lab at Harvard. And I'm going to present our paper, Dostoevsky, Better Space-Time Trade-Offs for LSM-Tree-Based Key-Value Stores via Adaptive Removal of Superfluous Merging. And I'm proud to say this is the longest paper title name in Sigma this year. This is joint work with my advisor, Stratos. So over the past 10 years or so, log-structured merge trees, or LSM trees, have become used for a wide number of applications. Today, they're the backbone of most key-value stores. They're also used as a backbone of some time series databases. They're used in relational databases. And they're actually just used as a general building block for various algorithmic problems. But in all these applications, LSM-Tree is typically used as a black box. This means that given an application workload, it's hard to know how to maximize throughput. But in this presentation, I'm going to argue that the situation's worse. In fact, given existing designs, it's impossible to maximize throughput. So I'm going to talk about why that is. The problem is suboptimal design. So I'm going to talk about why that is and what we can do about solving this problem. But before, I'll give some background on how LSM trees work. So the main design principle that LSM trees follow is to buffer application updates in main memory. Whenever this buffer fills up, we sort its contents by key, and we flush it to storage as sorted arrays that we call runs. To bound the overall number of runs that exist in storage, we sort merge them. And because we always take runs of similar sizes and merge them together to create something that's at least twice as big, these runs have exponentially increasing sizes, and LSM-Tree organizes them into levels of exponentially increasing capacities. In order to find a target key, we probe all of the sorted arrays. And in general, we have these fence pointers in main memory that allow us to find the relevant key range in each one of the runs with just one I/O. We typically also have Bloom filters to probabilistically allow us to skip probing runs that don't contain the key we're looking for. In this presentation, I'm mostly going to talk about the merge frequency of LSM-Tree. So the merge frequency strikes an important trade-off. The more we're going to be greedy about triggering merge operations, the more we're going to pay an overhead to execute those merge operations. But on the other hand, that's going to put a more tight bound on the number of runs that exist, and so it's going to bound our lookup cost. So we have this trade-off that we need to strike. And in general, all LSM trees implement one of two merge strategies to strike that trade-off. So one of them is called tiering and the other leveling. One is more merge optimized, that's tiering, and it's used by default in Cassandra. And one is leveling, that's more lookup optimized, and it's used by default in, for instance, RocksDB. So how do these work? So with tiering, for any given level, we just accumulate runs. And whenever that level, only when that level reaches capacity, we execute a merge operation, and then we flush the resulting run to the next level. With leveling, we trigger a merge operation as soon as the next run comes in. So as soon as a run comes in from the previous level, we merge it, and if the resulting run now exceeds the capacity of the given level, we flush that to the next level. So in general, the number of levels in LSM-Tree is log of n, where R is the size ratio between the capacities of the different levels. And so this means that with tiering, we have R runs per level, and with leveling, we have at most 1 run per level. And the size ratio is actually a really important tuning parameter. So if we set the size ratio to be really small, say we set it to be 2, in that case, the behavior of tiering and leveling actually converges, because at that point, any level can contain 1 run. Whenever the next run comes in, it immediately gets merged and flushed to the next level. So the behaviors converge and the performance characteristics converge. On the other hand, if we set the size ratio to be really high, the first level of the LSM-Tree is actually so large that it never reaches capacity. So in that case, the tiered LSM-Tree just degenerates into a log, whereas the leveled LSM-Tree degenerates into a sorted array, because whenever the buffer flushes, we just merge it into whatever is there. So we can actually take this space and we can map it onto a trade-off continuum between lookup cost and merge cost. So at the edges of this trade-off curve, we have the log and the sorted array. In the middle, between tiering and leveling, we have the case where the size ratio is very low, so their behavior converges. And then in general, from that point, we can increase the size ratio under either leveling or tiering to navigate this trade-off continuum. All right, so basically, all key-value stores today inhabit points along the space, and they can be tuned along this trade-off curve. But the question we ask in our research is, can we do better than this trade-off curve? So is there anything better beyond the trade-offs that existing systems strike? So in our paper last year, we showed how to push this trade-off curve once with a certain optimization. And in this presentation, I'm going to show how we did this once more with our paper Dostoevsky. But before I talk about Dostoevsky, I have to say a few words about Monkey, because our new work builds on top of it. So with Monkey, we looked at how to tune the Bloom filters of LSM-Tree. So in particular, we showed that given a particular main memory budget, the best way of tuning the main memory budget among the Bloom filters is to set the false positive rates to be exponentially decreasing for lower levels of the tree. With this, and the false positive rate is equal to e to the power of the number of bits per entry. What this does is it makes the false positive rates become a geometric progression that converges to a constant that's independent of the number of levels. And so relative to existing schemes, it shapes a factor of the number of levels away from point lookup cost. Okay, so by so doing, Monkey generally, with the same main memory budget, makes the sum of false positive rates lower, so it makes lookups generally cheaper, and it pushes the curve. And we now show another optimization to push the curve even further. But before I talk about this new scheme that we proposed, Dostoevsky, I have to do a problem analysis over the leveled merge policy. So I'm going to do an I/O breakdown of where the different I/O overheads arise due to different types of lookups and merge operations with leveling. And then we're going to spot a design problem. So for point lookups, we already know from Monkey that the false positive rates are exponentially decreasing for smaller levels. And that means that point lookup cost is generally dominated by access to the largest level of the tree, because access to that level is exponentially more probable. Okay, so point lookups derive most of their cost from the largest level. On the other hand, so in the same vein, long-range lookups, for any given target key range that your application wants to access, because the largest level is exponentially larger than the rest, most of the keys that you're going to be looking for are going to be at the largest level. And so access to the largest level also dominates cost for long-range lookups. On the other hand, for short-range lookups, we have to issue one random I/O to each one of the levels. So our cost is going to be log of n, the number of levels. And now, when we analyze merging, here comes the key. Merge operations at larger levels of the tree take exponentially more work to execute because they're exponentially larger. But on the other hand, they take place exponentially less frequently. And so in the long run, these things balance each other out. And merge operations do the same amount of work in the long run across all the different levels. Okay, so can we measure this cost? So to do that, we can look at the number of times that a given entry participates in merge operations in a given level before it flushes and before it fills capacity and flushes. So in general, a level begins as empty, and merge operations continue to happen until eventually R merge operations have happened, and at that point the level fills up. So each entry participates in R merge operations per level, where R is our size ratio. Okay, so that means that every entry gets copied R times per level, and if we sum that across all the different levels, we have R times the number of levels, log of n. And the key here is that this merge cost derives equally from across all the different levels. So now we have a nice cost breakdown of where all the different I/O costs come from, and we spot an asymmetry. Point lookups and long-range lookups derive their cost from the largest level, whereas for merging, we're doing the same amount of work across all levels. So this implies that all the merging that we're doing at smaller levels is excessive. It's somehow superfluous. It's not really doing much towards contributing to bounding our lookup cost. All right, so that's the insight. For point lookups and long-range lookups, most merging at smaller levels is superfluous. Now, this problem actually gets worse as the LSM-Tree grows, because we get more and more of these smaller levels where we're doing the same amount of work, but access to them is increasingly less dominant as the tree grows. So this leads to poor performance, because we're wasting I/O on these merge operations, but it also leads to lower device lifetime if you're using an SSD, because for SSDs, device lifetime is a function of the number of writes that you issue to it. Okay, so to solve this problem, we introduced Dostoevsky, which stands for Space-Time Optimized Evolvable Scalable Key Value Store. It's recursively defined. And it's very right optimized. So we had the tiered and leveled LSM-Tree designs before, and with Dostoevsky, we introduced a new design, lazy leveling, which is better for mixed workloads. So basically what lazy leveling does is it applies the tiered strategy for smaller levels of the tree and leveling for the largest level. And now, so for the largest level, for each one of them, we only perform a merge operation only when one of the smaller level fills up. But for the largest level, we trigger a merge operation whenever a new run comes in. So merge operations at the largest level are greedy. And now we can do an I/O analysis exactly the same way that we did before for leveling and see what we've accomplished by doing this. So for point lookups, if we optimize the memory across all the Bloom filters to minimize the sum of the false positive rates, we get the following false positive rates. So they're still exponentially decreasing, and access is still dominated by the largest level. But the main point is that the bound that we get on point lookup cost is the same as the bound that we had before for leveling. And the reason for that is that, so this is a really key insight. So the only reason that we get the same bound is because the false positive rates are exponentially decreasing for smaller levels. So lazy leveling really relies on this new optimization that we came up with last year. If it wasn't for that, then we would have to pay a heavy overhead for access to all these runs at the smaller levels. So for long-range lookups, access is also still dominated by the largest level because that still takes more work than the random IOs the few random IOs that we now have to issue at smaller levels. But for short-range lookups, here we incur our overhead. So we have a worse bound because we have to issue a random IO to each one of these smaller runs. But for merging, we actually get a win. So for merging, we now perform every entry participates in one merge operation at each one of the smaller levels, and at R merge operations at the largest level. So now we get a bound of R plus log of n. So this is better because before we had R times log of n, now we have R plus log of n. Okay, so these are our bounds, and now we can compare these bounds to leveling. So we see that for point and range lookups, the bounds are the same. For short range lookups, lazy leveling has a worse bound, and for merging, lazy leveling has a better bound. We can also make the comparison to tiering. So I didn't comprehensively analyze tiering in this talk, but the bounds for reads are all worse, whereas the bound for merging is slightly better because we're doing less merging at the largest level with tiering. Okay, so what does this mean? So if we actually plot all the different trade-offs for all these different schemes by varying the size ratio for each one of them, we get a curve that looks like the following. So if you only have point lookups in your workload, lazy leveling just completely dominates leveling across the board because we're doing a lot less useless merging. On the other hand, if you have a lot of short-range lookups, lazy leveling is actually going to get dominated by leveling. But as the target key range for these range lookups increases, lazy leveling is going to be increasingly more and more competitive because most of your overhead is, increasingly more of it will come from the largest level. Okay, so we have tiering, which is great for updates. We have leveling, which is great for short-range lookups. And we have lazy leveling, which is great for combinations of updates and point lookups. So what can we do about this? How can we leverage all of them in the right, appropriately for the right application? So to do that, we introduce a generalization of LSM-Tree called fluid LSM-Tree. So how does that work? So basically, in fluid LSM-Tree, we control the bounds on the number of runs at each one of the smaller number of levels, independently from the bound on the number of runs at the largest level. So we can begin with lazy leveling by default. And now let's suppose that we want to optimize for different operations. So let's suppose that our workload has a lot of short-range lookups and we want to optimize for them. So what we can do is we can start tightening our bound in the number of runs at smaller levels. And when we do that until the number of runs gets to 1, we actually just get to a leveled LSM-Tree. On the other hand, suppose we want to optimize more for merging. In this case, we can first of all go back to lazy leveling. And now we can start increasing the bound on the number of runs at the largest level. And when we do that all the way, we get to tiering. Suppose we want to optimize more for point lookups. To do that, we can get back to lazy leveling. Now we can actually take the size ratio and increase the size ratio to decrease the proportion of entries at the smaller levels. And that's going to be good for our point lookup cost. So overall, fluid LSM-Tree has 3 parameters: the size ratio, the bound on the number of runs at each one of the smaller levels, and the bound on the number of runs at the largest level. And that allows you to assume all the different designs that exist today, so lazy leveling, leveling, and tiering. And generally, Dostoevsky is a system that analytically finds the best tuning for these parameters of fluid LSM-Tree. So it does that by iterating over a closed form model and finding the best tuning with respect to a particular application workload and hardware. So how does all that perform in practice? So we made an experiment where we vary the proportion between point lookups and updates in the workload. And this is a log scale, so we increase point lookups at an exponential rate across the x-axis. So for leveling, performance generally increases as we increase the proportion of point lookups. That's because leveling is a read-optimized policy. For tiering, performance decreases because it's not very good for reads. It's much better for updates. For lazy leveling, performance actually is dominant across most of the space because it's better for mixed workloads. And Dostoevsky dominates all of these different designs because it's basically a superset of all of these different designs, and it can just assume the best design for any workload point. So how does Dostoevsky perform against systems out there? So we compared it to our system Monkey from last year, and for most of the space it performs better because it allows you to optimize more for these mixed workloads. We also compared it to a tuned version of RocksDB and a non-tuned version of RocksDB. And here it performs a lot better because RocksDB doesn't have that Bloom filters optimization. So reads are unnecessarily expensive. OK, so overall, we introduced lazy leveling, a new LSM-Tree design that doesn't do any merging at smaller levels and does greedy merging at the largest level. We showed that lazy leveling provides better trade-offs between point queries and merging. We introduced fluid LSM-Tree, a generalization of the whole space that can assume all the different designs. And finally, we introduced Dostoevsky to be able to tune fluid LSM-Tree for a given application workload and hardware. OK, so all of this is a part of the Crimson DB project that we have going on at the Data Systems Lab. And the goal of that project is to find the best possible performance and space trade-offs for any given application, workload, and context. So yeah, so there's the website, and stay tuned for more. Thanks very much.
So if you use different technologies at the different levels, say an SSD at the higher levels and a magnetic disk at the lower levels, how would that affect your system?
It's a great question. I don't think that there's generally a very good answer to that. I think that what you could do is you could look at, right, with magnetic disks, the cost, these devices have different properties, right? So disks are really great at sequential access, but the cost of reads and writes is basically the same. For SSDs, writes are significantly more expensive than reads. So what you can do for each one of these different hardwares is, you can start by putting your data on SSD, and you can try to make it, I would probably want to make it very write optimized. So we want to save on merge operations for SSD. Right, because you don't want the device to die. Whereas for the disk, eventually SSD is more expensive. Eventually things are going to flash to the disk. For that, I would make things a lot more optimized for reads, right? Because the merge operations can benefit from the large sequential bandwidth of the disk. So yeah, so I think that you could use this framework to come up with a design that kind of works best for the SSD and works best for the disk. Yeah.
Hi, excellent talk. I really enjoy it.
Thank you.
So I just want to comment that now with Surf in your toolbox, it kind of changes the game for the short-range queries. So it may push your frontier even down. So we need to talk offline.
Yeah, I definitely think that we need to talk. I think that there can be really, really great synergy there. I mean, I would imagine that the optimizations that we describe throughout our work with the Bloom filters would also, I would imagine, out of the box work with other types of filters. We haven't investigated that yet, but I believe that they could work with cuckoo filters, with quotient filters, and possibly also with Surf. So I definitely think there can be great research done in this area, and we should talk.
So from the talk, it seems that you are minimizing the amortized worst case cost.
Yes.
So what happens if the key popularity has some skew? So you are overwriting the same key again and again, so the inserts may not reach the last level even when you are inserting many keys. So in that case, actually, different levels might have different weight for the cost, overall cost. So what's the relationship between what happens when you are considering the common case and the key popularity distribution is not uniform, and it could be skewed.
Yeah, yeah, yeah. So I think it's a great question. I think that one thing that you actually might be able to do is, let's suppose that you have like a subset of the workload that's very intensely updated and read. This means that you're actually only going to be issuing your IOs to lower levels, to smaller levels of the tree, and there, because of the greater number of runs, you might get hit. So one thing to note is that the false positive rates at these levels are going to be so much lower, like they're going to be exponentially lower, so your point lookups are not actually going to suffer very much. One optimization that you could introduce is you could become increasingly, you can detect the point in your LSM-Tree where it sort of stops being write intensive, and then you can start being more greedy about merge operations as you go down. There's totally a lot of room for that. Yeah, thanks for the question.
Okay, let's thank once again.